All right, so now you should have a real good feeling with how the substitution method works, what we're doing with that. Of course, we're solving systems of linear equations, and we're basically saying, hey, if your variables are equal for that one point of intersection, you're just forcing the equation's hand. You're saying if you want to find the point where your variables are equal, where your coordinates are equal, let's call the variables equal. That lets us substitute and find the point. So basically, we're tricking the problem, working backwards. We can do that by substituting the variable from one equation into the variable from another equation. That's the idea. By doing that, you're saying these are equal variables. They're equal coordinates. That's going to create equal points. That's really easy to do when you already have one equation to solve for a variable. But what about when it's not? Is it easy? Can be. Is it hard? It can be. If it is hard, there's a better method for it though. So we're going to start looking at that, and we're going to start seeing the need for a different method here real quick. So let's start off with this one though. We have a system of linear equations, obviously. Here's the point. In order for the substitution method to work, you have to have one equation solved for one variable. Now, a lot of students ask, well, does it matter? Does it matter what variable I solve for? Not at all. Whether you find the x first and then give me the y, or the y coordinate first and then give me the x, it doesn't matter. You're still completing that ordered pair, that point of intersection, and that's what we're looking for. So, does it matter? No! And if it doesn't matter, pick the variable in either equation that's the easiest to solve for. Now, here's what I look for. So when I look for this, I look at the equation that I can add one thing to both sides. I like it when I have to add and not subtract because that eliminates a negative or a minus. So I'm looking for something that I can add to both sides that eliminates a whole term and leaves me with one variable. It's not this one. It could be. There's nothing wrong with subtracting 5x. You could totally do that. But I'm looking at this one. If I add y to both sides, I get x equals something that's all pluses and positive. I like positives. We all know that sign errors are where our biggest failings are. So we're not looking at that. Now, you probably have a question in your head. Well, man, I totally looked at that one. Am I going to get it wrong? Not at all. There's many ways to solve it. You could solve this for x if you wanted to. It's not going to be fun, but you could do that. What I'm looking for is the easiest variable that pops into your head where you're like, yeah, I can solve that in one step. At most, 2 steps and not getting fractions. That's a good choice for substitution. So when we do that, when we look at an equation and say, I want to solve this one. I want to solve that one for not y, because I don't want negative, for x. I need you to really get it that this is the same exact equation as this with a different look. But the look is important here. The look says, well, I've solved for x. Now, we just got through talking about it, but if I've solved for x and I'm looking for where these lines intersect, verify that's a line where they cross is our solution to our system of linear equations. I want to find the one point where these lines are equal, the one point that satisfies both lines. That point in both lines is going to have equal x coordinates. Let's replace this x with what this x is equal to. That says to these equations, I want you to find the point that's on both of you. So if I have a point that's on both lines, the x coordinates have to be the same. So we've solved one equation for one variable. We got it. It's solved for x here. It doesn't matter which one. I'm going to replace the variable in my other equation with what this variable is equal to. It's saying, hey, this x equals y plus 3. But if these x's are the same, then this x also equals y plus 3. That's the idea of keeping our coordinates equal, saying your points on both lines, your x coordinates have to be equal. So 5x, no, not 5x. 5x, well, if x is equal to this x, but this x is equal to y plus 3, it's kind of a transitive property. It says this x equals this x. Since this x equals y plus 3, this x also equals y plus 3. That's a substitution. It's replacing the variable in one equation with what the variable from a different equation is equal to. We're substituting this in for that variable. That's it. It gives us something with only one variable left. Oh, that's awesome because we can solve that. If we do by combining some like terms, subtracting, hopefully correctly, subtracting a constant, dividing, we find half of our point. We've always talked about what we're actually doing. We're finding a point of intersection. Points are two numbers put together that are ordered pairs. So we have half of what we're talking about. It's kind of nice. We have variables also that have different names. So we can say, hey, y equals -1. The y coordinate for our point of intersection is -1. That's awesome. Now let's find the x. When doing the substitution method, the best thing about it is that whatever you used to substitute, so that equation, whatever solved for a variable, is always solved for the half of the point that you're missing. That's cool. That should make sense. When we replace this variable with what this is equal to, we replace all the x's with stuff that has y's in it. That's cool. That also means that when we get solved for our y's, we can plug it in here and find the x. That's what we substituted anyhow. So we plug in -1. And we get to. That is the one point that's on both lines. That's the one point where our lines intersect. That also means that we can always check our work, and please do so before we go on any further. This point has to work in both lines, both equations. Now, one thing about checking your work, when you check your work, you should always check it in the very original problem you got. Because what if you screwed this up? What if you accidentally added y and got -y over there? That'd be a problem. So we always check these points in our original equations, not the stuff we used to substitute. That's where a lot of people say, I checked my work. I mean, I know it was right, but they checked it here. What if you make a mistake from here to here? It's not going to show up. So check this in these two equations. Make sure it works in both of them. We explored this before, how you can have a point that works in one equation and not in the other one. For sure. I mean, there's a lot of points on a line going on forever. Well, almost all of those points, all but one, is not going to work in another equation. So we're going to make sure this works in both. X is 2, I'm going to write that out. 2 minus -1. See, minus negative, that's at 2 plus 1 is 3. Hey, I know that works. That satisfies that equation. 5 times 2 plus -1. 10 plus -1, 10 minus 1 is 9. I know this point is on both equations. It did not take me long to actually check it. And I know for sure that's my solution to the system of linear equations. That's it. That's how substitution method works. Now the next one. I would like you to try it on your own. So I'm going to give you a minute, and I'm going to look at it for a little bit. Hopefully you're looking at the same thing here, but I'm going to pause for a second. I'd like you to see what equation has a variable that's easy to solve for. Then solve for that variable and try your substitution. Well, if I'm looking at it, these variables don't look easy to solve for. These variables, that one doesn't look that easy to solve for. I'd have to divide by -2. That's not fun. But that y, that does look easy to solve for. That's the easiest variable in either equation to solve for. And that's all I really care about. I'm not asking you to solve both equations for one variable, just one equation for one variable in order for this substitution method to work. I would pick this one. If we add 2x, we get y equals 2x plus 3. Do you still remember how to graph that? Do you still remember the slope is 2? The y-intercept is 0, 3, so you go up 0, 3, and then up 2 over 1. Do you still remember that? I hope you've been spiraling your information, going back and checking out the other material you've learned. That way you don't forget about the graphing stuff. So this becomes our new equation. And because we're trying to solve for the system, we're trying to find the point where they intersect. We're trying to find the point that has the same y values and the same x values, the same y and x coordinates. Well, what that means is that this y and this y have to be equal. So instead of having 7x minus 2y equals -6, I can have 7x minus 2y. These y's are the same. That's what the point of intersection says. The y's have to be the same. So do the x's. The y's have to be the same. If this y equals 2x plus 3, then this y also can equal 2x plus 3. So 7x minus 2y? No. 7x minus 2x plus 3? Yes, because that's what y is equal to from another equation. You're just setting them equal to say if these equations are equal, well, then the point we find is going to be the point of intersection where the equations are equal. And then we can solve. By the way, your ability to distribute is super important. Your ability to distribute and not make sign errors is really important. When we distribute, make sure you're distributing with the sign. So we get negative 2 times 2x, well that's negative 4x, I write a minus. Negative 2 times 3, positive 3, that's a minus 6. If I combine some like terms, if we add 6 to both sides, be careful on your signs here. Don't be seeing, hey, negative 6 and 6 is 0. It's really easy to do that. We're adding 6. So we have 6 plus 6, that's 12. If we divide by 3, we get x equals 4. Are we done? Is that where we stop? Well, if that's where you stop, you have half a point. You're going to get half the credit, but you're not done. We've just completed 1/2 of the point of intersection. What's great about substitution is what you use to substitute is also solve for the part of the point that you're missing. So plug in whatever you got from your solving, whatever you got from step number 3, plug it into the equation from step number 1, the one you solved for. So in our case, we're plugging in x equals 4. And it will complete the other half of your point. Looks like 11 to me. So our point of intersection for these two linear equations, these two things that make lines, the one point that's common to both of them, one that we said our x's have to be the same and our y's have to be the same, giving us the same point on both lines, is that point. That's our solution. Let's check it out. X has to be 4 and y has to be 11 and work in both. So if x is 4, let's try that. That's 28 minus 22. Let's see, 28 minus 22, that's 6. Whoa, that's a problem. Did we make a mistake? That would be good if we did. Oh, so we have an issue. So let's find out where we went wrong. So we plugged it in, that's not working for us. Let's see if it works here. So negative 2 times 4, that's 8. Plus 11, that's 3. So what's going on with this guy? We have a problem somewhere. Let me check my distribution. So that's negative 4, that's minus 6. We combined with this, we added, we got 12, we got 4. We plugged in 4 here, we got 8 plus 3, that's 11. So why is that not working? Do you see it? Where did I make my mistake? Can you find it? Hopefully you've been screaming at me for the last like 5 minutes because I did something real stupid. I did something coming down here, I forgot something. What did I forget? Can you find it right now? Because it screwed the whole thing up. All this is wrong, which sucks, but it's right here. I forgot to bring down a negative. So if you work this out and you got a different answer than me, good, because you should, because I messed it up. I'm not even going to edit this because I want you to see the logic in going back and finding mistakes. Because if I didn't do that, so maybe it's a good learning point for you. If I didn't check my work and I assumed I was right, I'd have something that obviously isn't. I'd have a point and I'd say, oh, that's point of intersection, but I didn't check my work, and so I'd be wrong. I'd totally get a 0 on a test from this. I totally would get it wrong on any problem I'm working on because I didn't go back and check my work. Now I went back and checked. I looked here. It works here. Negative 2 times 4, well, that's negative 8 plus 11. That's 3. Works here. Doesn't work in this one. I got this and said that's not, something's fishy. So that caused me to go back and look at my work and find a mistake. I forgot to bring down that negative. Almost all errors are just sign errors. Ugh. Kills you. So let's see. So if that's a negative, if I add 6, oh, now negative 6 plus 6 is 0. Look at that. And divide by 3, x is 0. I've completed half the point. I go back up here. It's not 4 anymore. This is 0. 2 times 0 is 0 plus 3 is 3. Now let's try the point 0, 3. Let's see if I'm right now. So if we plug in 0, 3, I'm going to try it here first. Negative 2 times 0 is 0. 0 plus 3 is 3. 3 equals 3. I know this point works in that equation. Let's plug it in here. 7 times 0 minus 2 times 3 equals 7 times 0 is 0. Minus 6, that's negative 6. Oh, it works. Now I know that I'm right. I hope that this illustrated, I made a mistake. I'm not going to hide it. I forgot to carry down my negative. It happened. It screwed the whole thing up. It caused me to look at it for like 3 minutes just because I forgot a negative. But it's important for you to see why in the world we freaking check our answers. Because if we don't, you're going to assume that you're right. And then if you assume it without checking it, a lot of times if you made a mistake, you're not going to catch it. So I wouldn't have caught it had I not checked my work. I checked it. Now I am sure that I found the actual point of intersection between those lines. I hope that makes sense, that you can really see what I'm talking about here. Now we're going to do a couple other ones. But before we do, I want to talk about one more thing. There might be some easier ways to go about doing some of these problems. You see, we're having to solve for y, we're having to solve for x, and when we have to solve for variables, that allows us this opportunity to make mistakes, and I don't really like that. So there's going to be another method coming up in a couple more videos where we won't have to solve for a variable. Pretty soon, this was pretty easy to solve for, and so is this one. But sometimes you don't have that. What if I had two equations that look something like that? That's not super fun to solve for. And then it leads to fractions, and then we have to substitute into fractions. Not fun. So we're going to get to this point of needing another method pretty soon. This next example illustrates that very well. Check it out. The pros of the substitution method are that it solves for a variable. That way when you get done with solving your equation after your substitution, you plug it back in. It's really easy. The cons are that you have to solve for a variable, and substitution method doesn't deal with fractions very well. Here's a big point. 2 big points. Number 1, don't use the substitution method on stuff that looks like that. That's crazy. You're going to see why in a second. So I would never use the substitution method on something that looks like this. I would use the elimination method. Now we don't know that yet, so I'm going to show you this, but I'm only showing this to you to get in your head that this method's not that great for this. Let's develop something better, and we will. So not a good method here. Here's why it's not a good method. You can't clear fractions in general with the substitution method. You have to solve for a variable and substitute in whatever you have. Then you can clear fraction at that. That's in general. Sometimes you can get away with it, but in general, you can't do that. So I would look at this and go, oh, man, both of these are nasty, but that's easier to solve for. I'm going to solve for this y. So I'm going to do it by adding y to both sides and subtracting 1. It looks like adding 1. So if we do that, we get I've switched sides on you. So we added 1, I put the y here, but we have negative 1/2 x plus 1 on one side, we have y on the other side. This does give you something to substitute. So we can replace this y with what this y is equal to. That's totally fine. What happens sometimes is that you have these fractions, so when you try to clear them, your y or whatever variable you're trying to solve for gets more numbers, more coefficients, and then you have to divide anyway, getting fractions back. It's not cool. So that's why I told you in general, we really can't clear fractions with substitution method. All we can do is get our 2x minus 1/2. Instead of this y, we're going to call it what that y is equal to. After that, we distribute. We solve it like normal. We distribute, and then we start clearing fractions. So we'd have 2x. You pull out your fraction button on your calculator if you're not very good at fractions. Negative 1/2 times negative 1/2 is positive 1/4. I'm going to put plus. Negative 1/2 times 1 is negative 1/2. I'm going to put minus. Now, I've shown you how to clear fractions on linear equations. We multiply every term, even the stuff that's not fractions, by whatever your LCD is. In this case, your LCD is 4. So I'm going to multiply by 4 on every single one of those fractions. I'm going to simplify the fractions that I can. I'm going to multiply what I have left over. So here, nothing simplifies. We have 8x. Here, the 4 simplify, I have 1x. Here, the 2 divides 4 2 times. 2 times 1 is 2, I have minus 2. Over here, the 2 divides 4 2 times. I'm going to have 13 times 2, that's 26. So we've gotten rid of our fractions, but you can't do it in general on substitution method until you get right down to here. That's a lot of fractions going on. It's not great, not the best method. If we combine some like terms, we get 9x equals 20, so wow, 28. Nasty. All right. X equals 28/9. Well, we have half our point. If we now plug this into our equation that we substituted for, we have simplify some fractions here. You can use your calculator. Negative 14/9 plus 1. Negative 14/9 plus 1. 1 is 9/9. So you use a common denominator there. That would be negative 5/9. So we have added y. We have added 1. We've got y equals negative 1/2 x plus 1. We use that to substitute. We distribute. Negative times negative is a positive. 1/2 times 1/2 is 1/4. Negative 1/2 times 1 is a negative 1/2. We have multiplied everything by 4. So every term gets multiplied by 4. We multiply here, get 8x. We multiply here, we simplify a fraction, we get 1x. Multiply here, we get 2 times 1, that's minus 2. Multiply here, we get 13 times 2. Well, that's 26. If we combine some like terms, we get 9x. We add the 2, we get 28. If we divide by 9, we get 28 over 9. Now, checking your work is not super fun, but it is possible. I'm going to go through that one time. Not awesome, but it is what we have to do. So let's check that here. If we multiply our x by negative 1/2, what we're getting is 28/9 times negative 1/2 minus negative 5/9. And oh man, I'm really hoping that's equal to negative 1. So we give it a try. So this would give us negative 14 ninths plus 5 ninths. Negative 14 ninths plus 5 ninths. Well, that's equal to negative 14. Remember, we have a common denominator, so negative 14 plus 5, that's negative 9, equals, oh, thank goodness. So that's equal to negative 1. I know that this point is on that, that equation. Now we try the other one. So now that we verified it's on that equation, let's try the other one. So 2 times 28 ninths so I'm going to plug in x 28 ninths, I'm going to plug in y negative 5 ninths, and I hope that we get 13 over 2. So let's try it. Man, so 2 times 28 ninths, 2 times 28, well, that's 56. Plus 56 ninths, plus over here we have, let's see, negative minus a negative. That's going to be adding 5/18. But we can't add that straight up. We need a common denominator. Let's multiply by 2 over 2. 2 times 56, that's 112. Plus 5/18. Let's keep on going. 117 over 18. So 117, man, what goes into that? Well, I know that 7 plus 1 plus 1, that's 9. Any number where you add the digits up and it equals 9, or a multiple of 9, is also divisible by 9. So I know that 9 goes into both those numbers. 13 times on the numerator, 2 times the denominator, that's 13 halves. Oh my gosh. Now I know that that point is on both of those lines. That's the point of intersection. Goodness, do you want to work with fractions like that? I hope the answer is a resounding no freaking way. I don't want to do that. That's what's going to give us the elimination method after we deal with some of these word problems and deal with substitution method. But there's another way. This is the dark side, okay? We don't want to deal with fractions like this all the time. So the pros of the substitution method: it does solve an equation for a variable. It's easy to plug into. The bad part is it will not destroy fractions for you. So you have to deal with fractions, and then after you do your substitution, you can eliminate them, sure, but elimination method is a little bit more concise as far as fractions are concerned. I hope that makes sense. I hope that you see the way that substitution method really works, and the fact that you need to check your answers before you move on, and in your original, because otherwise you're not really sure yet whether you have the point or not. I hope you watched the mistake that I made earlier, that you learn from that. Please learn from that mistake. We'll deal with some word problems in the next couple videos, deal with some applications of this. I'll see you next time.